Today, we want to continue talking about sequences, series, and power series. Our current game is to determine if a series converges or diverges. So we have entered the multiple choice portion of events. The game is going to be, I hand you a series, and you determine if it converges or diverges. Later this week, that choice will go from 2 choices to 3 choices, because there's going to be 2 different kinds of convergence. That will be really cool. Let's talk about what we know already. In a world with lots of computing power, this is pretty good, knowing what a brute force approach is. Just like knowing we can approximate a definite integral with area. And we can keep improving that approximation just by using more subdivisions, which is just calculating the function more often. This is good news in a world of massive amounts of computing power. So our sequence a series converges if the sequence of partial sums converges. This is our brute force approach. So we can imagine just setting a computer to figure out what the sum of the first million terms is, what the sum of the first 2 million terms is, what the sum of the first 3 million terms is, and see if those sums are approaching a limit. We don't always have this amount of computing power available, and we don't always want to tie up our machines for the amount of time it would take to determine if the series converges. We want to be able to identify whether a series converges or diverges just by looking at it. And so we've developed some tests. One of these is the test for divergence. If the limit of the terms is not 0, the series diverges. If the limit of the terms is not 0, then the series diverges. We thought about this in terms of the sequence of partial sums. If the limit of the terms was like 2/3, then the sequence of partial sums, each term will be 2/3 bigger than the previous one. And that will just, that sequence will diverge if you just keep adding too much to it. One of the things that we've noted with this is that just because the limit of the terms is 0, that does not mean that the series converges. It's possible that the limit of the terms is 0 and the series still diverges. So it's important that we recognize it's possible that if the limit of the terms is equal to 0, that the series might still diverge. My robot is in the way. Now it looks like it's doing some kind of swan dive. So it stands up straight, it looks down, and it looked up. And now it's going to spread its arms and dive. Oh, I should not do that because then I bend this all the way back, keep it out of the way. So it's like something has gone horribly wrong during the dive. He hit very badly. And now his neck has gone 180 degrees the wrong way. This turned really gruesome, really fast. What were we talking about? Oh, yes. So it's possible for the limit of the terms to be 0 and the series still diverges. Our favorite example of this is the harmonic series. the harmonic series diverges, even though the limit of the terms is equal to 0. One of the ways that we saw this was with the integral test. We take the terms of our series and we make a function out of the general term of the series. And then we look at the improper integral. We just take the term, make a function, integrate the improper integral from 1 to infinity. If 1 is no good because it's 1 over x minus 1, for example, then just start later. More important part is integrating to infinity. If that improper integral converges, then the series converges. If the improper integral diverges, then the series diverges. This is good. It gives us something to do. This is bad. We have to integrate. Pro, something to do. Con, we have to integrate. So I guess that depends on how you feel about integrating. The important result that we get from the integral test is P series. The series 1 over n to the p converges if p is greater than 1 and diverges if p is less than 1. If we think about the integral of 1 over n to the p, if p is greater than 1, then n stays in the denominator. If p is less than or equal to 1, then p gets moved up to the numerator, or we get natural log. We want to keep the n after integration in the denominator, because when we plug in infinity, I know we don't really plug in infinity, but when we plug in infinity, an n in the denominator will go to 0, but an n in the numerator or in a natural log will go to infinity. So this is related to the integral. So if p is greater than 1, that x to the 1 minus p will be in the denominator. And if p is less than or equal to 1, then x to the 1 minus p is in the numerator, or natural log. Or in a natural log, both of which will go to infinity. The reason that this is important is that we don't have to look at all the details of what's going on like we would have to in a rational function, as we would if we were going to integrate the rational function. So the reason that this is useful is the test that we left off with last time. We're going to think about what's going on in a series. The important stuff is happening when n is very large, when n is going to infinity. Doesn't matter what's happening when n is something small, like 100 or a billion. Doesn't matter if n is small like that. What matters is that n is going to infinity. So when we're looking at a function, we can kind of just look at the important parts of the function and determine that one series will behave like another series. That's very fishy language. One series behaves like another series. We have to quantify what we mean by that. Like the word fair. Fair doesn't actually mean anything in the context of just like one person. Fair is a variable definition. You can't say that this is fair and then go tell some other people what you decided fair is. Even if we all decided together what fair is, everybody in the room decides this is what fair is in Calc 2 class. There are a bunch of students that are not here, and we can't go to them and say we have decided that this is what's fair, because that's not how fair works. You know what I mean? That's why I'm not worried about things like fair grading. It's unilaterally decided. I decide what constitutes a sufficient grade, and then y'all kind of have to accept it. In fact, the entire rest of the world has to accept it. It doesn't matter who you get on your side. If I give you a B, you know what grade you're going to get? B. You know how many people you have to convince that you need to get it to change it to an A? One. Exactly one person, and it would be me. It does not matter who else you get to make the arguments that you should get an A. If I decide that you get a B, it's a B. It's almost like a baseball umpire. It doesn't matter if the ball went 6 inches off the outside corner of the plate. If the umpire calls it a strike, you know what? That's a strike. And everybody else has to cope with it. This is not an amount of power I'm really comfortable having. But there it is. You know what I mean? Yeah. So we got to quantify what we mean by behaves like. We'll have a sense about what it is, but we should be able to explain it. And that comes down to the comparison tests. Notice that these tests involve a comparison. So we're going to have two series. So instead of just saying let AN be a series, I'll say let AN and BN be series. We've got to have two to everything. Notice it says comparison tests. There's two of them. So first. So I'm going to make one series smaller than the other series. AN is going to be smaller. Notice that I didn't write series. It's not the series AN. This is just the terms. The terms of AN are always smaller than the terms of BN. This actually doesn't have to be for all N. It just has to be for all N after a certain point. But we're just going to say for all N because lazy. So notice that we've got a smaller and a larger series. If the smaller series diverges, then the bigger series diverges. That makes sense. We're adding up all the terms. If we make all the terms bigger, we're going to get a bigger sum. So if the smaller series diverges, then the larger series diverges. Going the other way, if the larger series converges, then the smaller series converges as well. This is just a statement of the comparison test. So what's going on here is we're making, we have a series in question, and then the other one is a known series, a series that we know about. So there's two series. One series is in question, the other series is we know. So note. So one of these is a known series. We know it converts, we know it diverges. Notice we only get two things. If the smaller series diverges, then the larger series diverges as well. If the larger series converges, then the smaller series converges as well. If the smaller series converges, we don't know anything. This test does not apply. If the larger series diverges, we get nothing. Because we just see the smaller one, well, it's going to be less than infinity. And that could just be infinity. So that gives us nothing. So for example, the series 1 over n squared plus 1. So 2 and 1 is, but 1 squared is 1. 1 and 1 is 2. So we should note that this series is not a p series. We're not looking at 1 over n to the p. These are not powers of some n. So we should notice this is not quite a p-series. 1 over n squared is a p-series. It's not quite a p-series, but we know it is very similar. 1 over n squared. It's very 1 over n squared plus 1 is going to be very similar to 1 over n squared. That's our nearest p-series that we can compare with this. And 1 over n squared, we know, converges. So we're going to conclude that 1 over n squared plus 1 converges by comparison with 1 over n squared. So the series 1 over n squared is a known convergent series. We look at 1 over n squared plus 1, we say plus 1 is not going to matter when n is large, like a billion. Billion isn't very much. A trillion. The way the argument would go, now this is just us convincing ourselves that the series converges. 1 over n squared plus 1 converges. This is not going to hold up in court. So if we're standing in front of Judge Judy, and I'll say, Judge, this converges because of 1 over n squared. That was enough to convince you. It's not going to be enough to convince Judge Judy. She's going to make fun of you on her show, and you'll be embarrassed. Of course, if you can stand that, that's a great place to get sued. All these people show up on Judge Judy and they have no arguments. But the show is going to pay them $5,000 for their appearance. And so if the other person wins $3,000, they still come out $2,000 ahead. All that had to happen was they got humiliated by Judge Judy on TV. She just yelled at them for a little while. That's the whole format of the show. You know what I mean? Like there's hardly ever really a decision to be made. Someone does a thing. They have no reason that they should have done the thing. And yet here they are in court. Because we need to be entertained. We need to look at that person and say, ha, we are above that person. We can kick down for a while. What I'm saying is that watching Judge Judy might not be the healthiest thing that we do. You know what I mean? It's an exercise in kicking down. Because we're always looking for that. Someone we can flex our moral superiority on. What a shit species we are. Is it a shit species or just a shit society? We could just blame it on society, but we're the species that made that society. So is there a transitive property of being shitty? That's what I'm saying. If A makes B shitty and B makes C shitty, does A make C shitty? Is that the conclusion that we can make? You know what I mean? Is there a transitive property? What are we talking about? Oh, yes. So what we can do here is we're going to compare 1 over n squared plus 1. The advantage that we have is that 1 over n squared plus 1 is going to be less than 1 over n squared all the time. So the argument would be, since 1 over n squared plus 1 is less than 1 over n squared, and since the series 1 over n squared converges, because it is a p series with p equal to 2, we can conclude that the series 1 over n squared plus 1 converges. By the comparison test. So 1 over n squared plus 1 converges to make the denominator bigger than 1 over n squared. If you make the denominator bigger, the fraction gets smaller. Each member of Ocean's 11 gets a bigger payout than each member of Ocean's 12. To make the denominator bigger, the fraction gets smaller. And the 1 over n squared converges. That's a known convergent series. It's a p series with p equal to 2. So there are other things that we might want to include, just in case someone calls us on this. If defense objects to just making this claim, we could say it's a p series with p equal to 2. And over here, as the denominator increases, the fraction will decrease. So 1 over n squared plus 1 will be less than 4. Good question. This is unfortunately fairly restricted, even though the idea is already taking shape. Because I need to be able to make this comparison. AN has to be smaller than BN, and BN is my known series. So if I make an adjustment, if I change my series, oh, I can't start at 1, I have to start at 2. Spelled equals wrong. Equals is the parallel lines. So in this case, we should suspect that this series converges just like 1 over n squared converges, because when n is very large, -1 is not going to matter. If you win $170 million in the lottery, you don't really care that you have to spend $1 on the ticket. If you do care that you spent $1 on the ticket, you are going to be broke very fast because you don't really understand how money works. So we should look at this, see the important bits, 1 over n squared, and say this converges because it's a 1 over n squared, even though it's not a p series. Once again, it's not quite a p series. But where it behaves like the series 1 over n squared, which converges. So looking at this series and taking the important parts out of the numerator and denominator, make us look at this as a 1 over n squared, and that converges because that's a p series, it's a known convergent series. So we should say we're going to suspect that this converges by comparison with the series 1 over n squared. A p series with p equal to 2. What we want to note here is that we can't use the comparison series, comparison test that we used in the previous example, because 1 over n squared minus 1 is greater than 1 over n squared. Because when we line it up with what we're making with the series that we're making the comparison to, it's greater than our known convergent series. Our known convergent series is the smaller one. If the smaller series diverges, we don't know if that means the larger series converges or diverges. Infinity is greater than some finite amount, or it could be just some other finite amount. So I can't make this direct comparison. The comparison goes the wrong direction. But we're still correct that this series converges by comparison with the series 1 over n squared. We just have to use a different comparison test. So here the comparison is in the wrong direction. So this is going to be a job for the limit comparison test. Oops. So we start off with a similar thing. We have AN and BN in series. One of these we know converges or diverges. Convergent or divergent, one of them we have to know what it does. The limit comparison test says the following. If the limit as n goes to infinity of AN over BN is equal to a non-zero constant, then both converge or both diverge. So if the series AN is in question, we look at the ratio of AN over a known convergent or divergent series BN. We make the ratio of those terms and take the limit as n goes to infinity. If that results in a non-zero constant, then we get both converge or both diverge. That's why we have to know what's going on in one of the series. An important thing to recognize about these tests for convergence is that with one exception, we have to know whether the series converges or diverges to run the test. We can't just be handed a series and say, well, I don't know what this series does. I'll do a comparison test. Because you got to pick what you're going to compare to, which means you have to know if the series converges or diverges. So we like to think these as tests. It's like, well, you put a series in, and then you run some tests to find out if it converges or diverges. But you can only run the test if you already know if the series converges or diverges. These are not tests to determine if a series converges or diverges. These are tests to prove that a series converges or diverges. So tomorrow we'll pick up with the limit comparison test, and we'll see how that worked in the previous example and how this is going to be useful moving forward. That's going to be it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.